In the last bit of videos, we went through and estimated a definite integral by using Riemann sums, but we were given the function of the that we wanted to take the area under. And I want to show you how we would solve problems if we were given a table of values instead of the function itself. So it's very similar, but a little bit different in some details about how we're actually going to calculate the area. So here's what's happening on page 500 of our notes is that we want to estimate an area using a midpoint sum in 3 intervals, and this is our table. All right, so at 0 we've got 15, at 4 we've got 6, blah 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 blah. So I made a graph of this just for kicks. So the graph looks like this, and so we want to find the area of whatever function this is. I mean, what is the function itself? Well, I don't know. Maybe it's something smooth like that. Maybe it's something very rough like this. I have no idea. Um, and so as far as coming up with an answer, an absolute definite integral for this, that's something we wouldn't be able to do. We just don't have enough data, but we can use our idea of Riemann sums to come up with an estimate for it. Okay, and so we want to approximate this using a midpoint sum and 3 subintervals. So there is a bunch of steps that you go through for this, and I have them listed right here. The first step is that we want to make sure that the table that we're measuring from goes from the bottom to the top of the integral. So for instance, in this example, we want to measure the integral from 0 to 25. And so that is this entire table. Sometimes it won't be, but this time it is the right size. We need to break the intervals into equal subintervals given the information that they have. So we need to break this into 3 subintervals. And here's how I want to do that and have it be kind of equal. That I think that I've got 1, 2, 3, 4, 5, 6 steps to get from the bottom to the top of this table. And so since this is 3 subintervals I want to break this into, each one of those subintervals should cover 2 of those gaps. All right, so my first interval is going to go from here to here. My second is going to go from here to here, and my third goes from here to here. So notice that these 3 subintervals all cover the same amount of data. Okay, and now from here, we're just going to use the Riemann sum formula that we did from before, except this time we can't be sure that the widths of all of the rectangles are going to be the same. Okay, so we need to compute the width of each subinterval. So this one goes from 0 to 7. So this rectangle is going to have a width of 7. The next one goes from 7 to 15. So 15 minus 7 is 8. And the last one goes from 15 to 25. So this third rectangle we're going to be measuring has a width of 10. All right, is this, this is the best information we can go with these 3 unequal subintervals, and that's going to be okay for what we need to do. We're only coming up with an estimate, but we can have this is what it's going to take to create the best estimate, the best midpoint estimate from the information we've been given. Now we want to figure out the height of each one of these subintervals, and we're going to use the same technique that we are asked to use. And it's going to work out almost the same way that it did in, with the examples we've seen before. So this is going to be a midpoint sum. So halfway between 0 and 7 is 3.5, but we don't know what f of 3.5 is. So what we're going to do is we're going to take the closest thing we have. So the value in the middle is the 6. Okay, so what this means is that if we're thinking about this, our first rectangle is going to be this high, or it's going to be this wide. It's going to go from 0 to 7, but it's going to have a height of our middle value. So if we were to graph it out, this would be our first estimate. Our second one is going to go from here to 15. Oh my gosh, I didn't even fill this in correctly. Never mind. Let's ignore that part. So the idea is that we're thinking about the midpoint values. Same thing here. So for the second subinterval, where is the height of this that we're going to use? Well, the value that we have in the middle of this subinterval is that f of 12 is equal to -10. Remember, negative heights is something we're not going to worry about too much. In our context, we're going to think about that as being the curve being below the x-axis. And we're going to count that as a negative area. And the last subinterval, we know that f of 20 is equal to 8. All right, and so our last step is going to be to calculate the areas and then add them together. So our first subinterval has a width of 7 and a height of 6. Our second subinterval has a width of 8 and a height of -10. And our third subinterval has a width of 10 and a height of 8. Okay, and when I put those values into my calculator, I get 7 times 6 plus 8 times -10 plus 10 times 8. If your calculator doesn't do the order of operations, don't type it in quite like that. Calculate each one and then add them together. But the estimated area under the curve, the estimated area under this oddly shaped curve, we're estimating that that's approximately 42. Okay, so that gives you one sense of how we can use the a table of values and not the function itself in order to estimate an area. So this is really valuable because, if you're doing scientific or engineering data that you're collecting, you don't really have the correct formula in very many cases. You're just collecting a bunch of data out in the field, and you're using that data to estimate areas for you. All right, in the next video, we will take a look at 2 more examples of this, and I will ask you to do the third one, and then there will be a lot of homework for you to do about it.